Hey everyone, so this video is going to be about homogeneous production functions. To understand the definition behind it, let me motivate it in this manner. So let us think about a particular production function, say f of k and l. Now suppose I tell you that instead of just having k and l as my inputs, suppose I decide to change the inputs by a certain proportion. So suppose I multiply it by some number t, okay? And I use t times k or t times l as the inputs. So, and t can be any number. It can be half, which means you're halving, you're using only half the inputs. It can be 1, which means you're just using the amount of inputs as they are. If t is 2, then you're doubling the inputs. If t is 3, you're tripling. T is 4, you're quadrupling, and so on. You get the idea. So suppose I'm changing the inputs by this particular proportion t. And I'm now asking, and I'm now going to be interested in understanding what happens to the output then, right? Because I'm changing the input combination, so what's going to happen to the output? Suppose the production function is such that when you change inputs in this manner, suppose you end up getting an output, say, which is very similar to what you started off with, which is just the original production function. And if your output is also going to be a particular, if the output is also going to be multiplied by a certain number, such as t power n, okay? And so which means that if I'm, say, doubling my inputs, and my output is either maybe halving or maybe just being the same, maybe the output is also doubling, maybe the output is not increasing by 2 times, maybe lesser than that, or maybe the output is, say, more than doubling. So, okay, let me repeat that. If I'm doubling my inputs and I'm looking at what happens to the output, is the output also doubling? Is the output more than doubling, or is the output less than doubling? And if I'm able to talk about the inputs and output in this particular manner, if I can relate them using an expression of this form, if I change my inputs by, say, a number t, if I multiply them by t, and if my output changes by t raised to the power n, okay, then that function is said to be a homogeneous production function of degree n. So that's just the definition. So for instance, if I have f of, say, 2k and 2l, and that gives me twice the output as what I would have with just the original level of inputs, then this function is homogeneous of degree 1. If suppose I have 2k and 2l, and I'm getting an output which is, so I'm doubling my inputs, but my output is only going up by the square root of 2. It's increasing, but by a smaller proportion. Then this function is homogeneous of degree n, and n is now less than 1. So suppose, I increase my output and if I double my inputs and I actually get that, my final output is now 4 times the original one. Inputs are doubled by output, but output is getting quadrupled. And this is a production function that is of degree 4. Now, you can begin to see, based on these very simple examples that I just showed you, how this number t to the power n tells us how it gives us some sense of this production function, right? If I increase the inputs, if I double the inputs, if my output also doubles, which is the case where n is equal to 1, then there is something called constant returns to scale, because the proportion is the same on the input and the output side. So if n is 1, you have constant returns to scale. If n is greater than 1, which is the third case that we saw here, if inputs double, but my output quadruples, it more than doubles, then you have increasing returns to scale. If n inputs double, but my output increases, but not, it doesn't double, it just increases by a lesser amount, which was the second case that we, the second case that we saw, which was this one. And when n is less than 1, you have decreasing returns to scale. And these all fall into the broad category of homogeneous production functions. And this is useful once you start doing a little bit more advanced micro theory, where you start discussing describing production functions based on their the nature of their returns to scale. And homogeneous production functions have a lot of mathematically attractive properties which make theoretical modeling easier. So we'll see one such property in just the next page. So that's the reason I'm familiarizing you to the broad idea of homogeneous production functions. So here I have a bunch of examples where I'm asking you to find the degree of homogeneity. So let's see what happens if we change the inputs by a number t. So instead of x and y, I'm just going to change the inputs to t times x and t times y. So I know how to compute this function. All that I have to do is just plug in x is equal to tx and y is equal to ty into this original production function. And what does that give me? I'm going to have this, right? And once you combine the t terms, you're actually just going to have t power 1, x power 1 by 3, y power 2 by 3, which is actually just t power 1 times f of xy. So this is homogeneous of degree 1. And t can be any number here again. You can double the inputs and the output will double. You can triple the inputs, output will triple. You can reduce inputs to half their original level, output will also reduce to half. So that's what homogeneous of degree 1 here represents. And I'm going to leave these two, the other two, as an exercise for you to compute the degree of homogeneity here. So one is increasing returns, other is decreasing returns. So try that out. Now, I want to show you one key result for homogeneous functions, and that's called the Euler's theorem, which tells you that if you have Q, the production function, if Q is homogeneous of, say, degree n, then you have this very neat expression that pops up, which is K multiplied by its marginal product plus L multiplied by its marginal product is actually just equal to n times the original production function. And if you recall, you actually proved something like this in one of the, we actually proved this when n was 2 in one of the examples in the isoquant video. So that was a homogeneous production function of degree 2, and we were actually able to prove this particular Euler's theorem there. Now, if that's the theorem, now we're not going to go into the intuition behind this or how it came to be, but I'm just showing you that this is the theorem. Now, when n is actually equal to 1, sorry about that. So when n is 1, this just collapses to an even neater expression where capital times its marginal product plus labor times its marginal product is actually just going to be total output. Now, if each input is going to be paid according to its marginal product, let's say. So suppose capital, the price of capital is actually going to be equal to how much addition it contributes to the output, let's say. So that's how let's say I'm going to be valuing maybe labor, the wage that I pay to the labor is going to be determined by how much that unit of labor, that extra unit of labor contributes to the output, and which is fair to say, right? So if you contribute to the output, I'm going to pay you wages equal to your contribution. So that is what I'm saying when I say if you value the input at their marginal product, then what happens to the left-hand side here? If you value these input, if each input is paid an amount equal to its marginal product, then the left-hand side is actually just going to be your total bill, right? MPK will be the price of capital, and MPL will be the price of labor. So the number of units of capital into its price plus number of units of labor into its price is just the total amount of expenditure that you will spend on the inputs. And so in this case, this just becomes the total expenditure on inputs, K and L. Let me K and L. And the Euler's theorem tells me that in that particular scenario, the total expenditure on inputs is actually equal to the total output that you're generating using those inputs. So the total expenditure that you put in is equal to the total output that you're getting out. And that is a very neat result, which will play a role when you want to have these elegant production functions that have these elegant properties, which makes subsequent analysis using calculus easier. And you're likely to see this only in more advanced courses, but I thought it's, it's useful for you to be familiar with the term homogeneity and what Euler's theorem means. So if Q has constant returns to scale, which is just another way of saying if n is equal to 1, then the Euler theorem tells us that the sum of all your factor payments, so K and L are inputs. The technical term is they're factors of production. So payments to these inputs are called factor payments. So sum of factor payments is just equal to your total output. And that's a pretty neat result. So that's all for this video. So I'll see you in class or in another video.